Question 23 appears pretty tricky at first, but if we remember a few key equations, it actually turns out to not be too difficult. So the problem asks us about the altitude of a satellite that is in circular orbit around Earth, and it's a geosynchronous satellite, meaning that the orbital period is synchronized with the 24-hour rotation period of Earth. And so looking at this problem, what immediately jumps out to us as the principles that this problem will be testing, well, we see that it's in circular orbit around Earth, and so that tells us that this probably is going to be some sort of a uniform circular motion problem. And we know from uniform circular motion that our acceleration is equal to v squared over r, where your velocity of the satellite is your v squared, and then the r is going to be the radius, but that's actually measured from the center of the Earth. So that's not quite the altitude, but that is the variable that we're going to be looking for here. And then the second equation that we have is the gravitational force equation between two masses. And so the only force acting on the satellite in this problem is the force of gravity from Earth. And so we've got that second problem I have listed here, where we have the force of gravity is equal to the gravitational constant times the mass of Earth times the mass of the satellite, divided by, again, that r squared, which is the distance from the center of the Earth to the center of the satellite. And then finally, we've got our F equals ma, obviously Newton's second law, which we're going to use to make those top two equations mirror each other. Let's start by looking at that top equation, where we have our acceleration is equal to the velocity of the satellite squared divided by the radius of the orbit, which is from the center of the Earth. And so if we pull that out, let's look a little closer at that velocity. We know that a velocity is just a distance over a time. And in this problem, we have both the distance the orbit travels and the time it takes to travel that distance, because we know that it completes a single rotation around the Earth in 24 hours. And so we know that the circumference of the orbit is our distance. So that's going to be 2 times pi times our big R, which is that distance from the center of the Earth to the center of the satellite. And our time period, we'll just call it T for now, but we know that that's 24 hours. So we can say that that is our velocity. So we can kind of get rid of one unknown variable there with a few things that might be able to cancel out down the line. Next, let's think about how we can use Newton's second law in conjunction with our first equation in order to set it equal to our gravitational force equation. So we have an acceleration in that first equation, and we know that Newton's second law tells us that force is equal to mass times acceleration. And so if we get the force from the acceleration on the satellite, we can say that that force is equal to the mass of the satellite, which is a little m, times that a sub r, which we can substitute for what we already have, that v squared over r, and then we can substitute it again with what we already have for v, leaving us with mass times 2 pi r over t squared, all divided by that big R. And so now we have two forces that we know equal each other, and we can set them equal to each other and begin to cancel some things out. So below, I just set our two forces equal to each other. We have our gravitational force equal to the force due to the centripetal acceleration of the satellite. And now we can begin to cancel some terms and move some things around to try to solve for that big R that is going to allow us to find the altitude of the satellite. We can start by just canceling out the mass of the satellite on both sides, because it's on both sides of the equation. Those are just going to cancel for us really nicely. Then I'll write it out a little cleaner down here. And I brought our t squared down to the denominator to make things a little bit easier for us. Next, we can distribute out the square and the numerator of the fraction on the right-hand side and get 4 pi squared r squared, and that's going to be over t squared r, and so we can cancel out that r on the bottom and the square up top. And then rewriting our left-hand side, we still have gm over r squared. So if we think back what we're trying to do in this problem, we're trying to find out the altitude of the satellite. So we want to isolate that big R. And so we can do that by moving our denominator over to this side and moving a couple other terms around. So on this side, we're going to be left with an R cubed. And then on the left-hand side, we're going to have GMT squared over 4 pi squared. And so to isolate R, flip around what side it's on, we're getting R is equal to the cube root of GMT squared over 4 pi squared. So in a technical problem, you could probably end the problem here saying that, my orbit is going to equal that equation that I just found out for the total radius from the center of the Earth to the satellite minus the radius of the Earth. Because it's not expected that you have memorized the gravitational constant and the mass of the Earth and the radius of the Earth. But for the sake of this problem, I'll write those out and we can get an actual number as a concrete answer. And so we have that our radius is equal to, and I'll plug in some numbers here for us. It's going to be a nice big equation. So that's our gravitational constant right there, 6.67 times 10 to the negative 11th. And then we've got the mass of the Earth, which is 5.97 times 10 to the 24 kilogram. And we've got the amount of time it takes, which we know is 24 hours. However, in this problem, we're working with seconds. So it's going to be 86,400 seconds squared. That's all going to be divided by 4 pi squared. And that is going to get us our radius. And so obviously you would not be expected to remember those numbers or do that quick math to convert hours into seconds in your head. Nor would you be expected to, do all these calculations out. However, we get that the radius of the Earth is about 6.371 times 10 to the 6th meters. So we can write that down here. And solving for that big equation we have above, we find that that larger radius is equal to about 42.2 times 10 to the 6th meters. And so if we subtract the two from each other, we can find that height of orbit is equal to our big radius minus our radius of the Earth. And that is going to equal about 35.9 times 10 to the 6th meters. And so, in conclusion, we find that the altitude of orbit of geosynchronous satellites is approximately 36,000 kilometers. And that is how you do this one. I hope that helped.